Okay, so hello everyone. Thank you for coming to the presentation entitled Microservices Tracing with Spring Cloud and Zipkin. My name is Marcin Grzejszczak. So before I'm going to go to the main topic, I'm going to say a few words about myself, because why not? So actually, I'm a developer working at Pivotal. Who knows Pivotal? Yay. Okay, who is using Spring Boot on production? Awesome. And who is using Spring Cloud on production? Okay, less awesome, but still very good. So yeah, I'm forming part of the Spring Cloud team, mostly focusing on the library that you're going to see today, so Spring Cloud Sleuth. Sleuth means a detective in English. Actually, there is such a word. And after the recent release, we were wondering how people will misspell it, because there's sloth, which is leniwiec in Polish, so I don't know. Anyways, I'm working in Spring Cloud, and I'm really fond of working with open source. So for those who have been to my previous talk like 30 minutes ago, I really encourage you to check the Accurus project, which at the moment is called Spring Cloud Contract Verifier, and became part of Spring Cloud. My Twitter handle is @Grzejszczak, and my blog is toomuchcoding.com. I guess it will be easier for the foreigners to go to my blog and then find my Twitter handle, because it can be very, very difficult to spell my name. Okay, so there's a warning. So there's going to be quite a few unfunny memes, so try at least to pretend that it's funny, or smile that I see that you're enthusiastic. So I apologize for the memes. So what is on the agenda? First, we're going to talk about what distributed tracing actually is. Then I'm going to show you how, with Spring Cloud Sleuth, you can correlate logs. And then I'm going to show you how to visualize latency with Spring Cloud Sleuth and Zipkin. OK, so let's get it started. Let's imagine that we have an ordinary system. So service 1 is calling service 2, and service 2 is calling service 3 and service 4. Typical production system, I guess your system on production looks similar to this, kind of. So let's simplify it even further on. So let's say that we have somebody on the UI clicking something, and he, let's say, forces some request to happen on the backend side. I mean, typical stuff. So in general, everything is awesome. So there's a user who's clicking stuff around, and he gets a response, and it's OK, right? So everything is great until it's OK. Stupid question, a stupid sentence. But actually, the problem starts when some exceptions occur, and like this is our job as developers to find the solution. So the user clicks, and he gets 500, right? He's unhappy. I mean, in general, he's furious. The table flip occurs, and issues are sent to some GitHub, or emails are sent from unhappy customers. And they're right, because they pay for the software that doesn't work. So then, I guess you know these two guys, but actually, we have to like jump into our suits as developers and jump into this pile of code in this gigantic system that we have and try to find the answer, like what happened, right? So we've been there, like having mud or another kind of substance, like under here, let's say over here, and we have to dig in to find the problem. So I lied to you, because actually your production system doesn't look like this, obviously. It looks more like this, right? So service 1 is deployed on, for example, 5 servers. Service 2 the same, 3 and 4 alike. So if a user says that there is an exception, or like shows you a screenshot of something not working, most likely like one of those guys blew up. So the question is, on which server and instance was the exception thrown? Right? This is the main problem. And one of the architects that I worked with had an idea that he would SSH to every single server of those, find the log, and grep for error. I mean, you can do that. I'm not saying, I mean, eventually you will find it. I even tried to find out on Stack Overflow, is there like a batch way to SSH over, on multiple machines and grep the logs, find them? I mean, you can do that, but there are better solutions, better approaches, one of which is distributed tracing. So in order to really, let's say, understand how to solve this problem, let's define some terms. So we have span, trace, logs, and tags. Let's focus on the two first terms. So what is a span? Span is a basic unit of work. For example, sending an RPC, so remote procedure call, is a span, is a basic unit of work, is a basic operation. So a span can be started and stopped. Span knows when it started and when it stopped, so it knows its own duration. Once you create a span, you have to remember to stop it at some point in the future. It cannot be like going endless. It has to be, it's a bounded operation. A span has a parent and can have multiple children, like typical situation in life. So this is the same case with span. Actually, the first span doesn't have a parent, so he's kind of sad. Oh, these jokes are so bad. Okay, we have trace. So trace is a set of spans forming a tree-like structure. I told you that the span can have a parent span and a child span. So altogether they form a tree. So this tree is a trace. So let's say that we have a bookstore, right? And one of the things that we can do in a bookstore is retrieve a list of available books. So let us assume that in order to retrieve the list of available books, we have to send 3 requests. So you send the first one, then you have 3 hops. So each of those hops will be a new span, whereas altogether they form one trace, right? So a hop equals a span, like a simplification. And a trace is the set of hops. So let's recap it. Let us assume that we come back to our situation with those 4 services. So this is our first service. There's no trace ID, no span ID. A request comes in. So what happens here is that the trace ID is set and span ID is generated. Those IDs are 64-bit numbers, but let's, for simplicity define them as letters. Actually, you can't see the colors here, but there's a color here. So right now, all the spans will be like in different colors. So a new span is created. Trace ID is set to X. Span ID is set to A. Now, service 1 is calling service 2. So service 1 is the client of service 2, which is a server, client server. So you can see that the trace ID is X, there's a new span, and there's an annotation placed, client sent. So when you're in RPC, the first thing that you have to do is to send the message, right? So you say, client sent, client has sent the message. Now, on the server side, you can see the same color, it's the same span, but on the recipient side, so on the server side, there is a new annotation, server received. So client sent, server received. Now service 2 does some new processing of the request, so a new span is created, the green one, and service 2 is calling service 3. So again, a new span, new ID, D, and client sent annotation. And service 3, server received. I mean, I could go like this forever, but let's start coming back. So service 3, let's say process the request. We have span ID with, that is equal to E, and we're coming back. So this span is closed. He finished processing of the request, and he's returning back the response. So just before he does it, a new annotation is placed, server sent, which means that the server side has finished processing the request. And as you could have guessed, once the client gets the response, a new annotation is placed, client received. All those 4 form an RPC. Client sent, server received, server sent, client received. We're going to focus on that later on. So you can see that all the time the trace ID is set to X, so it's the same. The same situation happens here, this for service 4, new color, new span, so we have F, G, and we're coming back. So at the end of the day, if that was retrieving of the books, you see that all the time we had the same trace ID, different spans, but what happens here is that the user gets in the headers the proper trace ID. Right? So trace is forming like tree-like, it's a set of spans forming a tree-like structure. And this is the structure like parent-child relationship. So the first span doesn't have a parent. B is the child of A, C is a child of B. And here you can see that we have 1 parent span and 2 children. Okay, and now, is it that simple? What I said is that, you know, trace ID is passed, tracing information is passed, but is it actually that simple? Actually, one does not simply pass tracing data. Because the question is, how do you pass tracing information or any sort of information between different libraries, different thread pools, when you're using asynchronous communication, different threads, right? So this is not trivial at all. Like imagine that you're using a library to, let's say, send HTTP requests in an asynchronous manner, so they are sent in a new thread. So basically what happens in that thread is like completely new in comparison to the previous thread. Like all the data is not shared. So you have to somehow push it all the time. So it's not that simple. And what happens is, for example, in this library, you forget to do proper instrumentation in terms of passing data, like tracing data. So what happens is that we have this case of ours, there's no trace. Let's say that you pass the trace ID like that, and you have a bug in your instrumentation library. So what happens is trace ID is set here to B, for example, here to C, there to D, and overall, for a single, let's say, operation, like retrieve the list of books, when you will then do, let's say, tracing analysis, it will turn out that you had 4 operations because you have a bug in tracing library, in the instrumentation library. So this is where we come in. So what you can do is use Spring Cloud Sleuth. So we described what spans are, what traces are, but the initial problem that we have is that we have exception thrown by, on production and an unhappy user. So we have to fix it. So one of the possibilities is to correlate logs. So to even think about this, Spring Cloud Sleuth takes care of passing tracing information between threads, libraries, contexts, like Hystrix, RxJava, REST template, Feign, messaging, Spring integration, Zuul. There's quite a few things that we already support out of the box that basically you don't have to do anything, and the tracing information is passed. So if you don't do anything unexpected, there is nothing you have to do for Spring Cloud Sleuth to work. So check out the docs for more information on what exactly we support and how to use it. Okay, so let's aggregate the logs. Let's assume that we want SSH to the machines. So if you're using Cloud Foundry implementation, for example, I don't know, from Pivotal, like Pivotal Web Services, you have your applications deployed in the cloud, they log, they have their logs. And in Cloud Foundry, there is a tool called Logregator that combines all the logs from all the applications, from all the servers into one place. Like, so the logs are aggregated in one place. But not everybody has Cloud Foundry. Most people, I guess, have their own servers on which they deploy stuff. So basically, you can harvest those logs, for example, by means of a tool called log/forwarder, which is now, I guess, renamed to FileBeat. So basically, your applications are creating their logs in a certain directory. Then this tool is scanning this directory and sends those logs somewhere. And this somewhere, it can be the Elasticsearch log/Kibana stack, for instance. So a logstash is a, let's say, it's a processor, so to speak. So it gets the logstash gets the logs, cuts them into pieces, stores them in an Elasticsearch, which is a database, and Kibana is the UI over Elasticsearch. Don't worry, we're going to play with that in a second. So how can you add Spring Cloud Sleuth when you're using Maven? It's fairly simple. It's enough for you to add the BOM to Spring Cloud dependencies. The current version is Brixton SR2. I think we're going to release Brixton SR1, sorry. We're going to release Brixton SR2 quite soon. And to add Sleuth, you just add Spring Cloud Starter Sleuth. If you use this approach, all the versions for the libraries are set for you. You don't have to set them. We're doing it for you. With Gradle, obviously, it's much nicer. I don't know how it will look like in Kotlin, but I guess quite similar. So you do dependency management, and you import the Maven BOM with Brixton SR1, and you add Spring Cloud Starter Sleuth. So our case looks like that we have service 1 with an endpoint start, those 2 hops, and service 3 is going to respond with hello from service 3. Service 4 will respond hello from service 4. And we're going to shoot back the response back to the user. Okay, so now, so this was the first case, and the second one will be, so that was the positive scenario, that everything works fine. But we're going to also take a look at the case that we have like initially, so the user does something and then there's an exception. So here now you will see the magic of my abilities of animation, so yay. So the requests are sent and there's nobody there, nothing there. So it's going to blow up. And that's what we're going to see. So time for the demo. Hopefully everything's going to work. So the first thing we're going to do is we're going to send a request to 8081 start. So that was the first case. As you can see, you can't see anything. No, you can. OK. So we have hellos. So you can believe me, it's not hard-coded. Really, there were hops underneath to the applications. OK, so here is the Kibana. So yeah, you can see something. So this is Kibana. So this is the UI where you can, let's say, check your aggregated logs. So what we're going to do is I'm going to import the default parsing of the logs. So here in those columns, you can see logs parsed in a certain manner. So before I show you that, let me show you the logs. So presentations, docs, build, and for example, service to log. So here you can see logs created in a very specific manner. So Spring Cloud Sleuth gives you a pattern of logging, which is quite good, in my opinion, because it contains stuff like name of the thread, which is often forgotten when you're logging your, like doing logging of your applications information. Because if you're doing concurrent programming and you don't even log from which thread the log came out, then you're going to have for sure a problem. Here you have, this is typical Sleuth's part, where you can find the service name, the trace ID, the span ID, and whether this particular span should be sent to Zipkin. I'm going to talk about this later. But this is like the log, and you can see the very same log in a much nicer format here. So let's say that we want to see what happened in our system. So we already know what a trace is, right? So the trace is an ID that is common for all the spans, let's say in one business, that took part in one business operation. So if you do here trace, like that, then we see all the logs from all the services. You can see here, service 2, service 1, service 4. So all the logs from different services in the distributed system that are, whose trace is common. So when I send the request at /.start, and there were 4 hops, all of the logs from all the applications related to this particular request are here. So let's say that we want to search only for the logs that have this trace and severity info, because I don't want to have like a lot of noise here. So next, what we can do is order it by time. I have some problems with the clock, so they actually might not be in the proper order. But if you don't have problems with the clock, then you would have all the logs ordered in a chronological, let's say, sequence. So you could search for every single log that happened from the beginning until the end of processing of the request. So actually, you can see here that we have, for example, this got response from service 2, hello from service 2. All the logs are there, right? So let's now focus on this problematic case where we had an exception. So let's check it out again. For sure, there is one with severity error. Whoops. Ah, sorry. Severity. What? Oh, because I didn't shoot it. Sorry. So it's working. It shouldn't be there. So right now I'm sending a request to the endpoint that will blow up eventually, because there's not going to be the recipient of the request. So I'm sending. I have a read timeout there. So I'm sending the request. Boom, like we have 500. So if we go back to Kibana, at the moment if I do severity error, yeah, I have it. Cool. So I already know the trace. Because let's say the customer service or the issuer of the exception told us that the exception occurred around like 20 to 2 p.m. So we can search the logs, search them by severity, find the trace, and then, again, search for all the logs with this particular trace. And that way, you can see exactly what happened on all the services chronologically that led to this following exception. And at the end of the day, we can see that, oh, here we have this error. Yeah, exception read timeout occurred while trying to send the request. So that way, we know what happened in a distributed system without SSHing, grepping, and stuff like that. You have it in one place, you can put it in a chronological manner, and actually, in my opinion, there's like, I don't know how can you live without such a tool in a distributed system in a like efficient manner. Okay, so this was the first part, so log correlation, right? So Spring Cloud Sleuth gives you the tracing instrumentation, so it passes the tracing information. It gives you a certain pattern for logging. If you go to Spring Cloud Sleuth documentation, over there you can find the log stash patterns on how to parse the logs. And also you can find information on how to do it with JSONs. Because actually here with, in this Kibana's demo, some services were logging to the log file and some in the JSON format. So it's like a proof that it's working fine. Okay, so that was the first case. Here you can actually, I guess, not see anything, but believe me that here is the output of all the applications on Cloud Foundry. This is the logregator tool that takes all the logs and puts them in one place. And this is the screen that you have just seen, but it was like, if the demo didn't go well, I could have shown you that. Okay, so we solved one thing. There is an exception. Somebody called us, said that it's something is not working. So this is a trivial case, because it's like a 0-1 situation. Something is not working. But there are more difficult cases. Well, for example, the system is slow. So we have a user who clicks around, nothing happens, and only then there is a response. And this is not that trivial to actually solve. This problem is not trivial, because in order to know which part is slow, you would have to start doing what? Stopwatch before every method? Every what? I mean, you would have to put a lot of code in your system to know exactly what was the time of, let's say, execution of some parts of the system. And then from these logs, you would have to somehow sketch a graph or something. So it's not that trivial. But yeah, and the question is, which of those services was slow? In a distributed system, everything can go slow. So how can we measure that? The answer is, again, related to distributed tracing nomenclature. So events, let's log some events. You have already seen quite a few events, 4 at least. So the first one is client sent. So the client has made a request. Server received. The server got the request and will start processing the request. Server sent. So upon completion of request processing, we put this annotation. And client received, which means that the client has successfully received a response from the server side. So now let's come back to the basics, like in high school. We have two parts of the communication, client and the server. Let us assume that we have a client side who has annotated the span with client sent at t equals 0 milliseconds, t equals 0, like during physics. The request was sent. After t equal 100 milliseconds, server received annotation was placed. Then after t, like this is like from the beginning, right? So after 300 milliseconds from the beginning, server sent was set. And after 450 milliseconds from the beginning, client received. So what are the conclusions? So the request started at t equals 0. It's obvious. It took 450 milliseconds for the client to receive the response, like the whole flow. Server side received the request at t equal 100 milliseconds. The request on the server side got processed in 200 milliseconds, right? You can see that. So why is there a delay between sending and receiving messages? Who knows? Why is there a delay? Why, when I send it here, I don't get it immediately. What? What? Which database? There's no database there. Like simple call. Network, exactly. 8 fallacies of distributed computing. We forget about that, and let's focus on the first 2. So actually those 8 define some assumptions that we take in terms of distributed systems that are absolutely not true. And those 2 are, let's say in this presentations, are most important. The network is reliable and latency is 0, specifically this one. Latency is never 0. It's not like you send a request and you get immediately the response. I mean, yeah, or the other way around, right? So it's not like that. And now it would be good to have a tool that would visualize this latency. To do that, we need 2 things, logs and tags. So logs, we have already sent, let's say defined them. I'm going to describe what logs are in more detail. So they represent an event that happened in time. So every span can have more or 0 or more logs, and every log has a name and a timestamp when it occurred. Event should have a stable name, some meaningful name, not an arbitrary one, because it, let's say, defines a notable moment in the lifetime of the span. Possible examples are, if you check the developer's Mozilla performance timing moments, representing browser page load events, it can be kind of similar. So here we have an example. For example, navigation start, unload event start, unload event end. So these are like notable moments in the life of related to page loading. And you could, when you're going to create your own spans, your own events, it should be something similar, a notable name for an event. So what are the main logs? Client send, we have seen that already. Client has made a request, the span was started. And now let's start playing with calculators, because if you take the server received timestamp and subtract from it the client-side timestamp, you get the network latency, right? 100 minus 0, latency is 100. Now, server sent, so when annotated upon completion of request processing. So if you subtract the server received from server sent, you get server-side processing time. Client received, so when he successfully has received the response from the server, if you subtract this value from this value, that value, so client received minus client sent, it's time needed to receive the response. If you subtract from this value, that value, so client received timestamp minus server sent, is the network latency over here. So with those kind of events, timestamps, you can, in a much easier way, visualize the latency in your system. For debugging purposes, you can also have something called a tag. So a tag is a key-value pair, where every span can have 0 or more key-value tags. They don't have any timestamps. It's just a simple value, a key-value pair. Example of default tags in Sleuth are, for instance, message payload size. So when you're sending a message, we will provide you a tag with information. What was the size of this message? What was the method, for example, of the HTTP call? And if you're using Hystrix, we're going to tell you what kind of command queue you were using. So the question, the main question is how to visualize latency in a distributed system. Let's say that the user told us that the system is slow. How can we measure that? The answer is Zipkin. So Zipkin is a distributed tracing system. Actually, it's run as a separate process. You can run it as a Spring Boot application. You just do Java jar and it's running. It helps you gather timing data in order to troubleshoot latency problems, especially in microservice architecture, but it's not only the case. In one of the companies that I've been working, we had it also in the monolithic app. And it represents the calls or like span duration by means of horizontal bars. The longer the bar is, the longer the request took to process. So how does Zipkin work? We have our applications. Now you already know what spans are, so it will be trivial for you to understand. So the applications are sending spans to things called collectors. So there's a collector or a bunch of collectors that are taking those spans and they store them in the database. And then when you go to the UI to check like the latency issues, when you click around, the UI queries something called an API that accesses that database. So that's the thing. So how can you integrate Spring Cloud Sleuth with Zipkin? Of course, we are taking care of passing tracing information, because without that, it's not going to work. Like, you have to pass the tracing information between threads and contexts and stuff like that. And then, when you close a span, so some operation has been finished, we are sending that span for you to Zipkin. And we can do it in two ways. One is via HTTP. You have to add the Spring Cloud Sleuth Zipkin dependency. And the other via Spring Cloud Stream. Spring Cloud Stream is an abstractor over messaging in the microservice world. So you can use Rabbit, for instance, to send those spans. You can also run the Zipkin collector as a Spring Boot application. So you can have multiple Zipkin collectors, and if you plug in the UI dependency of Zipkin, each of those applications will have also the UI. So integration with Zipkin is very easy. With Maven, again, the bomb with Brixton SR1, and Spring Cloud Starter Zipkin. This is the default starter for the HTTP-based communication. And in the Gradle, it's the same stuff, Spring Cloud Starter Zipkin. Now hold it. What you should ask about is, if I have billion services that emit gazillion of spans, will I not destroy Zipkin, like those collectors? You will flood them with messages. And actually, you might. So the first thing is whether the applications will sustain the load. And the second thing, whether the database will accept that many data. If you have seriously bazillion of those spans, you'll have to put them somewhere. So the question is to trace or not to trace. And the answer is that you can sample. So what does it mean? You're not taking into Zipkin every single request. By default, we send only 10%. So inside the logs, everything will be instrumented. You will see trace ID, you will see span ID, all of that. But only 10% of spans will be sent to Zipkin. It's because Zipkin can be used in a very good way to track consistent issues with latency. If you have incidental ones, you know, if you're in those 10%, you're lucky you're going to find it, right? If not, then you have a problem. You have to check out from the logs. Of course, if you think that the load is not that big, you can change it, or you're doing demos, you can change the percentage, for example, to 100%. Then every single span will be sent to Zipkin. But you have to remember that, let's say your applications will not, like your database will sustain the load, and you will have enough of Zipkin collectors for in order to process all the spans. You can also register a custom sampler if you want to do something more, let's say, complex in terms of sampling. OK, so let's do something cool. We're going to write a new service, a Devoxx service. It's a branded service specifically for this conference. So what it's going to do is going to send the request to the first service, and we're going to track the latency issues in our system. So I'm going to go to the site called start.spring.io. As Josh Long would say, this is the site that you should go when your children are crying and when you feel alone, or whatever, something like that. So when you're going here, in order to, let's say, make you feel more happy, you're going to generate a Spring Boot project. So I'm going to do a Devoxx project with what? Web, Actuator, why not? They're giving it for free, so Zipkin client as well. So I want to send the spans via Zipkin, via the HTTP. OK, so I'm generating the project. It's there, Devoxx with a 1. Since I am a MC guy, I'm going to unzip it like this, like a mouse. OK, and now I'm going to import the project. Don't look at this. Where is it? Presentations, Devoxx. OK. Oh, the internet. OK. So let's open the project. Resolving dependencies. Yes, thank God. OK. We're entering the presentation mode. So we have a simple scenario here. We have a project, nothing fancy, Devoxx application. What is cool is that all the dependencies are set for you. You don't have to do this. And since we are hardcore, we're going to do build snapshot. Yeah. We're going to work on snapshots. OK, so we need to write a controller. So what can we do? We can write a Java class and do a Devoxx, branded Devoxx controller. So we need a REST controller, since we're doing, obviously, constructor injection, because everybody does it, right? Who is using field injection? Oh, my God. You're trolling. You're not doing that. I know you. So we have the constructor injection over here. We have to annotate it with auto-wired. And let's do a request mapping here at Devoxx endpoint. String Devoxx is awesome. And we're going to do something, let's say, related to microservices. So as you know, with microservices, the worst thing you could ever do, and we're going to do that, is to hard code the address and port, and I'm going to specifically do that, only for the sake of presentation. Here you should do some service discovery or something like that. I'm not aligning this string for a purpose. You're going to see that in a second. Yeah, response. OK. So that's almost it. What else we have to do is provide some properties. So the first thing will be Spring application name. We will say it's like maybe Devoxx. I'm not good at naming. I never remember this sleuth thing, percentage. Yeah, so it has to be 10, because we want to sample all the requests. And some server port that my browser remembers, so 966. OK, so if, OK, I have forgotten about the bean here. REST template, return new REST template. OK. So theoretically, it should work. So we run it. Any questions until now? Because we have like 5 seconds until it boots. No? OK. So it's working. It's working. So let's shoot a request at localhost 9096 Devoxx. Yay! We have the responses. OK. Come back. OK. So let's finally take a look at this mythical Zipkin. So this is the Zipkin UI, where you can see that we can find a trace or sketch the graph of dependencies. I'm going to show you the dependencies in a second. So you can search for all services that I have played around with for the last week, because the default span is week. How did I do that? Oh, sorry. The default time is a week. So let's check it out. Let's do find traces. And here we have the trace that I've executed less than a minute ago. So let me click it. And right now, you can see a flow of messages in time. Oh, OK. So to the left, you can see the services that took place in this trace. So we have Devoxx service, service 1, 2, 3, and 4. Here you can see the initial name of the endpoint that we should, so HTTP Devoxx. If we click it, oh no. Oh, sorry. If we click this one, the next one, we can see all the 4 events that I told you about like 15 times during this presentation. So we have client sent, server received, server sent, and client received. You can see that the Devoxx service was talking to the service 1. And you can see at which relative time which service did what. Like here, for example, annotated with client sent. Here you have the tags. So I know that a message was sent to the localhost/start with a method get. So these are the annotations and tags. What is really awesome is that immediately you should ask, like, assuming that those services, like 2, 3, and 4, did nothing, why is it so slow? Why, for example, this bar endpoint in service 3, service 2, service 3, why was it so slow? And the answer is because I put a sleep there. But I know this, you don't, but immediately you can take a look at this project or like this trace and say, what is going on? Why is it so slow? So this is the first thing that allows you to visualize latency. Another thing is like, for example, service 2 here has the client sent. Why server received is here? Why is it so slow? Again, you have maybe some network latency issues or something like that. This is the new feature in snapshots. That's why I wanted to go towards snapshots. This is the client side. So service 1 is calling service 2 at full endpoint. And on the service 2, you can see the name in the controller that accepted this request. So then you can check out that there is a method named called service2 method in controller. So yeah, so this is like exactly the way you can, in an easy way, visualize latency. Here you can see that the whole trace took over 1 second to process. You have a lot of information about this here. When you click the dependencies, oh, I should not show you this second guy. Let me tweak it a little bit. Yeah. So here you can see that I was too lazy to sketch the graph that I showed you initially related to your system looks like this. I took it from Zipkin, because Zipkin can sketch the graph of your dependencies like post factum. So you choose the time for which you want to draw the dependency graph. You click Analyze Dependencies, and it shows you what kind of dependencies were there. If you click on one of the services, you can see that, for example, it's using service 2, and in the provided time, there was one call from service 1 to service 2. And right now, I'm going to show you how to create custom spans. So let's go here. And one of the things that we have to do in our lives is do something very important. So we're going to do it. We create this method, and we're going to create a span. In order to create a span, we need something called a tracer. A tracer is an interface from Sleuth that allows you to create spans. So what we're going to do here is first we're going to do span equals null. Yeah, this one. We're going to do a try catch. Catch because of Java's fantastic requirement to catch everything. And finally, we're going to close tracer. We're going to close the span. So as I told you, when a span is started, it has to be closed. So we're doing span, tracer, create span, and it's an important span. So we're going to name it important span. Now, we're going to add a tag. So with a tracer, you do add a tag, and let's say that I'm doing this talk like on the 25th conference. So I want to know, when I'm in Zipkin, that I want to filter only for the conferences, for example, the Devoxx conference. So I'm going to do it here, like conference equals Devoxx. Now, we're going to do something hideous, so we're going to sleep for 2 seconds. And in the meantime, we're going to log an event. So an important thing that happened in this system. So for example, during this talk, you fell asleep. So this is an event. Now, after 1 second, somebody told you that you're snoring, so you woke up after this time. Okay, so yeah, we're calling that. Let's run it again. So here you can see how easy it is to create a span. This span is wrapping, of course, you would have more intelligent business logic over here, but you would wrap it in a span, so you would know when it started, when it finished. So if we shoot again at this endpoint Devoxx, it's waiting for localhost. Okay, it took more time. Okay, it's done. So we can go back to Zipkin. We can do find a trace. And less than a minute ago, we have another trace. And here, now you can see our important span. So we created a new important span. Immediately, if you take a look at the trace, it turns out it's very long in comparison to the other ones. And if you click it, you can see those notable moments in the lifetime of a span. So after relative time of 2 seconds, you fell asleep. And after relative time of 3 seconds, you woke up. So this is how you can define custom events that allows you to let's say, debug the latency or what kind of problems you're searching for in here in Zipkin. And also conference Devoxx here, right? So how can I filter? You go back here, and here you can put some annotations query. So you put conference Devoxx. You click it, and you have this specific one. If I'm going to search for conference whatever, I'm not going to find anything, right? So you can easily find some stuff related, basing on the tags. Okay, and the last thing that I'm going to show you is how you can do stuff in terms of checking, let's say, fixing stuff with parallel computing. So let's say that, let me turn the page, that we have an executor service here. Executor equal executors new whatever cache thread pool. To do some magic that I'm going to do in a second, we need also a guy called span namer. As you can, let's say, guess, it's used for naming spans, so the name is pretty good. Now let's do a future. Future equals, we're going to submit a job because this, let's say, very important job is very slow. So let's wrap it in the future. So let's do a trace runnable here. We're going to put a tracer here, a span namer, and a new runnable. So we're going to put this very important thing over here. I'm going to do some hacking. OK. Tracer get current span. I'm not going to create a new span. I'm going to reuse the current one. OK. So I'm doing something very important here. And I'm going to do generate, come on. Do a toString here. So since in Java you cannot annotate anonymous classes, you have to do some other stuff. So basically to name a runnable or callable that you're instantiating, you have to provide the name in a toString. That's our solution. So here's going to be a toString sad span. OK, so right now, I'm going to do a get here. OK? Seems like a good idea, because obviously I'm doing it like in parallel, right? So let me run it again. Who thinks that we're going to have a significant improvement in performance? Oh, thank God, not a single person. That's good. So we're going to shoot it again. We have to wait for some time because I have a lot of sleeps there. And let us find the trace again. OK, less than a minute ago. First, we have this toString sat span here, right? And it's taking the very same time to execute, like obviously, because I'm stupid and I did a very stupid thing. So basically here we are blocking for 3 seconds to retrieve the response. Sorry, for this method to finish. And also here we're blocking because I put a lot of sleeps in other services. So like poor man's work to make it work faster is just to move it here. Because this guy will block for the response, but this guy will, in background, still calculate, right? So if we run it again, let's wait a sec. Let's shoot a request again. OK. And let's check it out. So find traces, less than a minute ago. Looks much nicer, doesn't it? So right now, you can see that this long-running request or long-running method started first. It's running behind the back. And here we were running all those hops and requests. That's why you can immediately see that those kind of nested structures are possible candidates to move them to the left, right, to make them more parallel. OK, actually, I don't even know how much time I have, so I'm going to finish. So a recap. So this is what you could see. This was the start. This was the end of the trace. This is the total duration. So it took, let's say, for example, in this case, 2 seconds. Here you have a client, so service 2. And those are notations that you could see. Client sent, client received. Service 4 was the server for service 2. So server received and server sent annotations were here. Here, the difference is the latency. Maybe it's good, maybe it's not good, right? It's up to you. I mean, it depends on how, what exactly happens in your system. Here, we know that there's a hop, so most likely it's not good. And here you can see the very same elements inside your, when you click on a span, so you take a look at events and tags. So difference between the relative time is a latency. So, who of you has seen my presentation a year ago about beer brewing and microservices? Okay, quite a few people. So basically the same app that was used for beer brewing is now used for end-to-end testing of Spring Cloud applications. I have rewritten it completely to use Spring Cloud, and we have around 10 business applications there, and we're also checking if tracing works. So this is sketched graph of calls between those services inside the brewery app. And I had to change the name, so there's no aggregator anymore, because it was impossible to spell by foreigners. And this is the call of graphs. It's about 155 spans to brew the beer. And even though you can't even seriously read it at the moment, you already see that this is pretty long, right? Something is wrong, I guess. So this is exactly what Zipkin is for, that even if you don't know exactly the system, you can assume that you have a, let's say, a span that takes a very long time. Why is it so, right? Okay, so the summary. Log correlation always allows you to match the logs for a given trace in a distributed system. Distributed tracing allows you to quickly see latency issues in your system. You just take a look and you see some potential problems. Zipkin is a great tool to visualize the latency graph and system dependencies, as you could see. And Spring Cloud Sleuth integrates in a nice way with Zipkin and grants you log correlation. Okay, so that would be it. So brace yourselves, questions are coming. So in the meantime, I will put this slide because there's a bunch of links that you can like take a picture of. Especially the first one is interesting because if you have Vagrant and you run, if you clone this repository and you run get ready for conference, all the code that you have seen, all the apps, will boot up automatically. So you're going to have Elasticsearch, you're going to have all the 4 apps, you're going to have Zipkin, and I'm curling the request, so you have some entries in Kibana already and in Zipkin. So clone it, play around with it, and time for questions. Go ahead.
Is there some other key for Zipkin? Because it's one of the most important things.
No, there is not, and it's actually kind of deliberate because it's a tool used to like debug issues, not to be alerted on. But it wouldn't be much of a problem to for the crucial parts of your system that you're interested in, wrap it in a let's say code-hell metric, and then like I presented a year ago, you can send it into Graphite and then have an alerting tool, for example, Siren, for which you define a metric name and the threshold levels. And then Siren, for example, checks that, in the case of brewery, it was the threshold of ingredients ordered. So if the level of ingredients went below some value, on Slack, we sent like an information that, hey, you went below some values. So these are, in my opinion, 2 different tools.
Is there a built-in assumption that the services share the same time? Same global time?
Actually, I can barely hear you. So maybe, yeah, try it. Is it an assumption that what?
Okay, so is it a built-in assumption that the services share the same global time?
Yes, yes. You would have to ensure that on your servers the time is the same, right? In terms of a clock, there is this tool, I don't remember, NTP or NT, whatever, I don't remember, that allows you to synchronize, let's say, clocks. So you should use that. We have an issue in Sleuth, for those who don't use it, to provide sequence number, right? So even though the clock is bad, you still can order via sequence, but it's not implemented yet. Any more questions? Over there? Oh, sorry.
A hypothetical situation. You have a microservice deployed on 5 instances, for example, and one is overloaded. What I didn't see.
And one is what?
Overloaded.
Overload, okay.
What I didn't see in the log format, in the log4j, there was no information about machine ID, for example.
You will have it, good question, you will have it here. So if you click on a log, you have the machine. In my opinion, in my case, it's localhost because it's on the Docker, sorry, on a Vagrant, but you would have it. So there was a question here, I guess.
Is there any limitation on the protocols used between the client and the server side, like
in terms of communication between services or Zipkin?
Between the services and between the, for example, the client, the database, or the file system operations.
Okay, so basically we support, in terms of communication between systems, we support messaging and HTTP at the moment. So we're supporting REST template, Feign, as an abstraction for sending calls. In terms of messaging, we support basically Spring integration and Stream. So if you're using like only JMS with JMS templates, you have a problem, but it's not a problem that we cannot solve. Right? Like there weren't many, let's say, requests for adding support for JMS, but basically it would be adding an interceptor or something like that. Like before sending a message, put the headers. When you got the response, or let's say when you pulled the message, retrieve the response and put the tracing information into the context.
And maybe another one. Have you measured any like performance impact of the tracing?
So we're checking that. We have in our Jenkins, with Jenkins DSL, the guys are going to talk about this in a second, about Jenkins DSL. So we've created some jobs. One of the jobs is that it runs both JMH and Apache JMeter to test what kind of impact we have on the performance, and it's rather neglectable. In terms of, for example, synchronous HTTP, it's 1 millisecond at most, because when we're calculating the let's say the overhead, the millisecond was the least possible value that we could have had. So, yeah, so that's it. More questions? Okay, so thank you very much.